Part A of these notes is going to cover radioactivity and an intro to nuclear chemistry. You will have to find the video for Part B, or the video for Part B will be separate, and that is going to cover atomic notation and nuclear reactions. All right, so radioactivity and an introduction to nuclear chemistry. Feel free to kind of take a minute and read all of this. We are kind of just looking at what does it mean for something to be radioactive, and so things like atomic power plants, treating food with radiation, using radioactive americium-241. That is something that is like the chemistry behind how those smoke detectors work, and looking at how can we do imaging using radioactive elements. These are all some of the uses of nuclear chemistry in our lives. And again, here is an introduction. Make sure you read this through. Really, our focus here is that when transmutation happens, an atom of one element is turning into an atom of another element. And so that transmutation. And emitting a particle, whether it's a nuclei or other radioactive particles, is called radioactivity with that. Our focus of chemistry throughout this year has been talking about stability. And when we've looked at stability in the past with kind of our non-nuclear chemistry, we've been looking at electrons and how are our atoms going to pair together and form bonds so that they become more stable based on their electrons. Now we are going to look at, well, isotopes, and we'll talk about what those are again. Isotopes are made from different amounts of neutrons in the nucleus, and those differing amounts of neutrons can also make atoms unstable. And so we're looking at now, what if it's things in the nucleus that are leading to instability, and how can those things change with that? And why is this important? Radioactivity, that process of the nucleus emitting particles, whether it is a proton, a neutron, and other different particles or energy like gamma rays. Those things can be used in medicine, and so they have a lot of benefits for our society, but they can also have serious hazards and risks to human health. So, reminders about our atomic structure, and I referenced some of it up above. Atoms are composed of protons, neutrons, and electrons. And in the nucleus, we have our protons, which have a positive charge, and our neutrons. And so those are in the nucleus here. And again, that name, nuclear chemistry, we are going to be looking at those things that are in the nucleus. So far this year, we have focused on, well, how do compounds form to make our electrons more stable? And those are in the orbitals that are around the nucleus. And so we're switching our focus now to that chemistry of what's happening in the nucleus. And this is kind of everything I've talked about. We've looked at how do these different reactions occur, a double displacement reaction occurring, so we get compounds that are more stable. But in that nuclear chemistry, we're looking at how the nucleus is going to react. So we might have one element, like uranium, and that element is now splitting into two different elements, like thorium and helium, where each of these individually are more stable. And how is that happening? Their nuclei are changing, which is how we get different elements. Whereas before we just saw, I had hydrogen here and I have hydrogen after. It's just changing what it's paired with. Same thing with my chlorine. So atomic stability, all chemistry is occurring because atoms are changing and rearranging to become more stable. Atoms that are found in nature are either stable or unstable. And so a stable atom, it has forces that are balanced between the protons and neutrons in the nucleus. Unstable atoms, the forces between the protons and the neutrons in the nucleus are unbalanced. And another term for unstable is radioactive, because it's going to go through a change. And radioactive might be a term you have heard before, but maybe not understood the meaning of. So as we talk about atomic radius, that trend of thinking of how big is our atom, as we were looking, that increased as we went to the left. Again, we have less protons as we go to the left, which means those electrons surrounding it weren't able to be held so closely. So we had our smaller atoms on the right side. And then the radius is increasing because we have more energy levels with that. And so in reaction, so far, we've worked mostly with our smaller atoms. We've focused on our carbon, nitrogen, we've got our calcium, and a lot of our kind of atoms that were kind of closer to the top or closer to the top right corner. Heavier atoms, those like uranium, polonium, iridium. So a lot of those atoms that are down here or down here, those are less stable. And so they're not going to actually form compounds with their, based on their electron instability. They are going to form, they are going to try to adapt and become more stable based on what is inside their nucleus. Let's do a little review of isotopes. So what is the difference between atomic mass and mass number? If we look at our periodic table, we have the atomic mass down here. And that atomic mass, if we look at something like lithium, that is 6.968. But you can't have a partial proton or a partial neutron. And so that atomic mass is the average of all isotopes of that atom, whereas the mass number is the actual mass of that specific isotope with that. And so we get that mass by doing protons plus neutrons. So isotopes are the same element, meaning they have the same number of protons. So if I was looking at, let's say, lithium, remember we get that atomic number is telling us our protons, but we might have a lithium with 3 protons and 3 neutrons to give us a mass of 6, or 3 protons and 4 neutrons to give us that mass of 7. So that's where we get that average from. So different numbers of neutrons, which lead to that different mass. And so same thing, same element means that same protons. So we might have that variation in neutrons, which leads to those different masses. So if we look at carbon 14, 12, and carbon 13, as I look, here's carbon on my periodic table. Carbon, it says 6 here. We have our atomic mass is 12.01, but each of these carbons, if something is carbon, that means that it's going to have that same number of protons, which is 6 protons. This notation, though, is going to tell us the name, and then the number after that is telling us the mass number for that specific element. And so the mass number for carbon 14 is 14. And so how do I find, I'm not using the mass number of 12 that's on my periodic table, I'm using that 14. Mass is protons plus neutrons, so I'm going to go 14 minus 6 to figure out, well, how many neutrons do I have? So I have 8 neutrons in that isotope. Carbon 12, well, that means my mass number is 12, so 12 minus 6 is going to be 6 neutrons. Carbon 13, well, that has a mass of 13, so 13 minus 6 is going to give me 7 neutrons. So we can see these are all isotopes. They have different numbers of neutrons, which lead to their different masses. Electrons are not our focus when we're looking at nuclear chemistry, really, because if the nucleus is unstable, the electrons are kind of going to be an afterthought to that. We're not going to have electron changes and nucleus changes at the same time. So all of these are neutral, which means protons, which are positive, and electrons, which are negative. Each of these would have 6 electrons in order for them to be neutral atoms, because no charge was told. So which isotope is the least stable and why? This is how we see different carbons are going to be stable and want to get to that stability. And as we look at it, we've got, and thinking of back to our slide where we talk about stability. Forces are balanced between our protons and neutrons, or forces are unbalanced. Well, I've got 6 and 8 for my protons and neutrons. I've got 6 and 6, 6 and 7. Well, I would say that carbon-12 is the most stable because we have that equal number of protons and neutrons. So carbon-14 has the biggest difference because there is the biggest difference in the protons and neutrons. And so carbon-14 in carbon dating, that's what is used because carbon-14 is the least stable of those carbon isotopes. All right. You are going to continue your notes using the crash course video. And then when you are done with that, come back for part B, which is going to look at actually writing nuclear reactions.